Access to clean water is a foundational infrastructure prerequisite that drives significant economic returns. It is the catalyst that dictates a community's capacity for growth. Historically, waterborne pathogens like cholera and typhoid have acted as rapid destabilizers. When these diseases spread through a local water supply, enable women to transition from manual water retrieval to paid employment or vocational training. That recovered time also secures educational retention. When children spend less time sick or fetching water, school attendance stabilizes. For older girls, nearby water and sanitation facilities are the primary factors in determining if they can finish their education. By cutting healthcare spending and expanding the labor pool simultaneously, clean water allows capital to circulate back into local commerce. The savings on medicine and the increase in productive hours create a compounding financial effect. This shift generates a calculated 7-to-1 return on investment. Every dollar spent on the infrastructure creates $7 of realized economic benefit, proving water is a powerful multiplier. To capture those economic returns, modern engineering has pursued a specific mandate, guaranteeing the absolute molecular purity of the water supply. Traditional purification relies on high thermal energy. Boiling water for at least 1 minute effectively destroys bacteria and viruses, but sustaining that temperature requires substantial fuel inputs. Other methods introduce chemical halogens, tiny amounts of chlorine, iodine, or bleach to neutralize biological threats. While effective, these additives change the water's chemical makeup. Industrial engineering offers a high-tech alternative, precision filtration systems designed to physically extract pure water molecules without relying on thermal energy or chemical additives. If high-tech systems can guarantee perfectly pure water, why are they not the immediate default solution for every community facing a water crisis? To understand the modern approach, we must look at how traditional bulk purification works. These systems sort water based on macroscopic physical properties, rather than microscopic molecular exclusion. Large treatment plants rely on coagulation and flocculation. Chemicals are added to the water, causing tiny, suspended pieces of dirt to stick together into larger clumps. Because these clumps are heavy, they sink to the bottom of the tank in a process called sedimentation, leaving the clear water separated on top. Other methods use biological filtration. In a biosand filter, a cultivated layer of microorganisms grows on top of sand layers. This biofilm actively preys on and consumes pathogens as the water passes through. While effective against dirt and some bacteria, these systems struggle to capture dissolved chemical compounds that remain suspended in the fluid. Achieving absolute chemical-free purification requires moving beyond bulk separation to highly engineered physical barriers. This brings us to semi-permeable membranes. These materials act as screens with microscopic holes. Utilizing these membranes requires significant force. High hydrostatic pressure is used to drive raw water directly against the synthetic barrier. This cross-section shows the structure of the membrane. The microscopic pores are engineered to exact dimensional thresholds, creating a strict physical filter. Macroscopic dirt and sediment particles strike the surface and are instantly halted, as their physical dimensions exceed the size of the holes. Biological pathogens, including large bacteria, similarly fail to breach the dimensional threshold. Even microscopic parasites and viral agents are entirely excluded by the strict tolerances of the structure. The pores are so tight that even dissolved chemical compounds are blocked, isolating the target molecule. Only pure water molecules possess the precise dimensions necessary to squeeze through the membrane and reach the permeate side. This absolute physical exclusion creates a chemically perfect output. However, achieving this microscopic precision introduces severe resistance into the overall system. When we shift focus from the pure output back to the raw input, the volumetric cost of this process becomes apparent. Forcing fluid through microscopic holes imposes a substantial flow rate penalty. These systems clean water much slower than other operational methods. This resistance results in volumetric inefficiency, a mandatory constraint where large amounts of water are required just to operate the system. This diagram illustrates the intake ratio. Reverse osmosis systems require drawing in 4 liters of raw water. The system yields exactly 1 liter of purified water, while the remaining 3 liters are diverted into a rejection pipe. The rejected water leaves the system as a highly concentrated brine, carrying all the contaminants blocked by the membrane. Contrast this with traditional municipal operations, which process vast volumes of water without generating extreme rejection rates. In arid regions where raw water is scarce, throwing away 75% of the intake volume is mathematically untenable. Pushing water through these tight pores also leads to the long-term physical degradation of the hardware itself. Continuous operation inevitably leads to membrane fouling. Blocked dirt, particles, and biological growth like algae accumulate directly onto the microscopic pores. Fouling increases the system's operational burden. To maintain safety, parts must be constantly monitored, subjected to frequent cleaning cycles, and replaced at a significant cost of time and money. Additionally, there is a biochemical consequence for the human populations drinking this overpurified output. Because the filters are strong enough to block nearly everything, they indiscriminately strip away healthy, essential minerals, specifically calcium and magnesium. Losing these minerals makes the clean water taste flat. More critically, it removes a vital dietary micronutrient source from the local population. While these systems offer high molecular precision, their trade-offs include slow production, high waste ratios, and frequent fouling. Engineers must match the filtration tool to the specific socioeconomic reality.